Hello there, and welcome to The Sleepless Scientist, a quiet place in the cosmos where your thoughts can unwind and knowledge becomes a soft lullaby for the night. Tonight's journey will take us into one of the strangest places the universe has ever created, the inside of a neutron star. But before you settle in and get cozy, I'd love if you could take a moment to like this video and subscribe, only if you truly find these quiet explorations enjoyable. And when you're ready, leave a comment to let me know where in the world you're listening from and what time it is for you right now. It's always such a gentle joy to see all the places we gather from, each in our own little slice of time. Now, feel free to dim the lights, maybe turn on a fan for a soft background hum, and let's gently begin our journey into the hidden heart of neutron stars together. And if your mind begins to wander, that's perfectly fine. Let it drift. We'll still be here, quietly unfolding the story. There is something comforting about the idea of stars. You've likely seen them countless times, scattered across the night sky like quiet, distant lanterns. They feel steady, reliable, almost eternal. And in a way they are, but only for a time, because stars live, and eventually they die. You've probably heard that before. It's one of those facts that becomes so familiar it almost loses its meaning. But if we slow down for just a moment and really sit with that idea, something begins to shift. A star is not just a light in the sky. It is a balance, a quiet, ongoing tension between two forces. On one side, gravity, always pulling inward, gently but relentlessly trying to compress everything into a smaller space. On the other side, something warmer, more active, the energy released from nuclear fusion deep in the star's core, pushing outward, holding the star up. For millions, sometimes billions of years, these two forces remain in harmony, a silent agreement. Gravity pulls in, fusion pushes out, and the star simply exists. But this balance is not permanent, because eventually the star begins to run out of the fuel that allows it to push back, and when that happens, gravity, which has been patiently waiting the entire time, begins to take over. Now, here's where things become interesting. Not all stars die the same way. Some stars, like our Sun, live long, relatively gentle lives. They burn slowly, steadily, using their fuel carefully over billions of years, and when they finally reach the end, their death is quiet, almost graceful. They expand softly into what we call a red giant, shedding their outer layers into space, leaving behind a small, dense core about the size of a planet, a white dwarf, a kind of quiet ember, slowly cooling over time. But not all stars are so peaceful. Some stars are born much larger, much heavier. Their gravity is stronger from the very beginning, and because of that, everything inside them happens faster, more intensely, more violently. You might think that having more fuel would allow these stars to live longer, but the opposite is true. Because their cores are under such immense pressure, the fusion reactions inside them burn much more rapidly. What a smaller star does slowly, a massive star does in a rush. It's a bit like two candles, one small burning gently through the night, and one enormous, blazing so brightly that it consumes itself in a fraction of the time. These massive stars may live for only a few million years, a blink of an eye compared to stars like our Sun. But during that short life, they go through something extraordinary. Deep inside their cores, they begin to fuse heavier and heavier elements. They start with hydrogen, just like the Sun, then move to helium, then carbon, then oxygen. And step by step, each stage requires more pressure, more heat, more intensity. And each stage becomes shorter. What once took millions of years begins to take thousands, then years, then months, until eventually, in the final moments of the star's life, everything accelerates, faster and faster, like a quiet build-up that suddenly becomes a rush. And at the very centre of it all, something begins to form, a core made of iron. Now, iron is not just another element in this story, it represents a kind of limit. Up until this point, every fusion reaction inside the star has released energy, helping to push outward, against gravity. But iron is different. Fusing iron does not release energy, it consumes it, and that changes everything. Because now, for the first time in the star's life, the outward push begins to weaken, the balance starts to break. Gravity, no longer opposed in the same way, begins to pull inward more strongly, and what follows happens incredibly fast. So fast, in fact, that it's almost difficult to imagine. The core of the star, which may be thousands of kilometers across, begins to collapse, not slowly, not gently, but in less than a second. It shrinks, rapidly, dramatically, until something that once spanned a region larger than a planet becomes compressed into something closer to the size of a city. And as this happens, the very nature of matter begins to change. The empty spaces inside atoms, the vast regions where electrons once moved freely around nuclei, begin to disappear. Everything is pushed closer together, closer than it has ever been, closer than it was ever meant to be. And this is the moment where we begin to leave behind the familiar world, the world where matter behaves in ways we can recognize. Because what comes next is not just a smaller star, it is something entirely different, a place where atoms can no longer exist in their normal form, a place where the rules that govern everyday matter are pushed to their absolute limits. And as we follow this idea just a little further, something remarkable begins to emerge from that collapsing core. Not a quiet remnant, not a fading ember, but an object so dense, so extreme, that even the laws of physics seem to pause and stretch and adapt to hold it together. A neutron star, a place where matter is no longer arranged in atoms, but in something deeper, stranger, and far more difficult to imagine. And to understand what really happens inside such a place, we need to go just a little deeper into that moment of collapse, where everything familiar begins to change. If we stay with that collapsing core for just a moment, before everything gives way completely, there is a story unfolding inside the star that is both quiet and urgent at the same time. A story of change, of transformation, and of time slowly slipping away. Inside a massive star, long before its final collapse, something remarkable has been happening for most of its life. At its centre, matter has been steadily transforming. Hydrogen, the simplest and most abundant element in the universe, has been fusing into helium. This is the same process that powers our own sun, releasing a gentle, steady flow of energy that pushes outward and keeps gravity in balance. But in a massive star, this stage does not last nearly as long, because the greater the star's mass, the stronger its gravity, and the stronger the gravity, the more pressure builds in the core, and with more pressure comes higher temperatures, and with higher temperatures, fusion speeds up. So while our sun might spend billions of years quietly turning hydrogen into helium, a massive star moves through this stage much more quickly, almost impatiently, as if it already senses what lies ahead. Eventually, the hydrogen in the core begins to run low, and something subtle shifts. The core contracts slightly under gravity, heating up even more, until it becomes hot enough to begin the next stage, helium fusion. Now, helium atoms begin to combine, forming carbon, and then, as the temperature rises further, carbon itself begins to fuse into heavier elements like neon and oxygen. Each stage follows the same pattern. Fuel is used up, the core contracts, temperature rises, a new kind of fusion begins. But there is a quiet detail here that is easy to miss, and yet it changes everything. Each new stage lasts less time than the one before it. Hydrogen burning might last millions of years, helium burning perhaps hundreds of thousands, carbon burning maybe hundreds of years. And as the star moves deeper into its final stages, the timescales shrink dramatically. Oxygen burning might last only months, and silicon burning, the final stage before collapse, can last just a single day. A single day. After millions of years of stable life, the star suddenly finds itself racing through its final moments. It's as if time itself begins to compress. What once unfolded slowly now rushes forward, and deep in the centre, layer upon layer begins to form, like the rings of an onion, each shell surrounding the next. On the outside, hydrogen still fuses into helium. Just beneath that, helium becomes carbon, then carbon becomes oxygen, then oxygen becomes silicon, and at the very centre, iron. A dense, silent core of iron atoms growing steadily larger. Now, from a distance, this might still look like a functioning star. It still shines, it still radiates energy, but inside, something has fundamentally changed, because iron marks a boundary, a limit. Up until this point, every fusion reaction has released energy, helping the star resist its own gravity. But iron does not behave this way. If you try to fuse iron into something heavier, instead of releasing energy, it absorbs it. It's like trying to push a heavy object uphill rather than letting it roll down. And so, when the core becomes dominated by iron, the star loses its ability to generate the outward pressure it depends on. Fusion, which once supported the star, begins to fail as a source of strength, and gravity, which has always been there, waiting quietly, begins to take over. At first, the change is subtle. The core contracts slightly. Pressure increases. Temperature rises. But unlike before, this increase in temperature does not lead to a new energy-releasing fusion process. There is no next stage to rescue the star, no new fuel to ignite. And so, the balance that held the star together for so long begins to slip. Now, something even more surprising begins to happen. As the core grows hotter and denser, the light inside it becomes incredibly energetic. So energetic, in fact, that it begins to break apart the very nuclei that were once formed through fusion. Iron nuclei, which took millions of years to build, are suddenly torn apart into smaller pieces. Protons, neutrons, fragments of what they once were. This process is sometimes described in physics with technical terms, but we can think of it more simply. The star is undoing itself. Everything it carefully assembled over its lifetime is now being taken apart in moments. And this matters, because breaking apart these nuclei consumes energy. Energy that the star can no longer afford to lose. So not only is fusion no longer supporting the star, the processes happening inside the core are now actively removing energy from the system. It's as if the star is both losing its strength and having it quietly drained away at the same time. And then, another transformation begins. Under these extreme conditions, electrons, those tiny particles that normally exist in wide, diffuse clouds around atomic nuclei, are forced closer and closer to the centre, closer than they would ever naturally move, until eventually something remarkable happens. Electrons begin to merge with protons, forming neutrons, and releasing nearly massless particles called neutrinos. These neutrinos are incredibly elusive. They pass through matter almost effortlessly, slipping out of the star, carrying energy away with them, an immense amount of energy. In fact, most of the energy released during this collapse does not emerge as light. but as this invisible flood of neutrinos streaming outward in all directions. And all of this, the breakdown of iron, the loss of energy, the transformation of particles, is happening while gravity continues to pull everything inward, faster and faster. The core becomes more compact, more dense, more extreme, until the collapse can no longer be described in terms of ordinary matter at all. The familiar structure of atoms has already begun to disappear. The empty spaces are gone. The boundaries between particles blur, and the star, which once felt stable and steady, is now on the edge of something completely new. If we follow this process just a little further, we begin to reach the moment where the collapse itself is suddenly interrupted, not by heat, not by fusion, but by something far more subtle and deeply quantum in nature. A resistance that does not come from energy being released, but from the very rules that particles must obey. And it is here, in this brief and extraordinary instant, that the neutron star is truly born. If we stay with that core just a little longer, something begins to happen that is both sudden and almost impossibly fast. Up to this point, we have been watching a gradual story. Layers forming, fuel being used, time slowly speeding up, but now the pace changes completely. Because once the core becomes dominated by iron, and once the processes inside begin to remove more energy than they provide, there is nothing left to hold gravity back in the same way. The balance is gone, and gravity, which has been quietly present all along, begins to take full control. At first, the collapse might seem almost gentle, a slight inward motion, a subtle shrinking. But this illusion does not last, because as the core contracts, something very important begins to happen. The density increases, and as the density increases, gravity becomes even stronger, and as gravity becomes stronger, the collapse accelerates, faster and faster. It becomes a kind of feedback loop. The more the core shrinks, the more strongly it is pulled inward, and the faster it continues to shrink. Within a fraction of a second, this process becomes dramatic. The core, which once spanned a region larger than a planet, begins to collapse inward at extraordinary speeds, speeds that approach a significant fraction of the speed of light, not quite reaching it, but moving far beyond anything we encounter in everyday experience. If you try to imagine it, it might help to think of something falling, not through air, not through water, but through space itself, with nothing to slow it down, everything rushing inward at once. And as this happens, the structure of matter begins to break down even further. We've already seen how atoms lose their familiar form, but now even the nuclei themselves, which once felt solid and indivisible, are pushed into conditions they were never meant to endure. The distances between particles become incredibly small, so small that the idea of empty space inside matter almost disappears entirely. It's no longer a collection of separate atoms, or even separate nuclei. It becomes something more continuous, more compressed, more unified, and in the middle of this collapse, another quiet but powerful transformation continues. Electrons and protons keep merging, forming more and more neutrons, until gradually the matter in the core becomes dominated by these neutral particles. Neutrons, particles that carry no electric charge, and can therefore be packed much more closely together. But even neutrons, as small and unassuming as they may seem, are not infinitely compressible. There is a limit, a boundary that cannot be crossed, and that boundary does not come from heat. It does not come from radiation. It comes from something much more subtle, a rule built into the very nature of these particles. As the core becomes denser and denser, The neutrons are forced closer together, closer than they would ever naturally be, and at some point they begin to resist, not because they are pushing back in the way a compressed spring might, but because they are not allowed, by the laws of quantum physics, to all occupy the same state. It's a bit like trying to seat an infinite number of people in a room, where each person must sit in a slightly different position, with a slightly different arrangement. As the room fills up, it becomes harder and harder to fit anyone else inside, not because there is a physical wall, but because there are fewer and fewer available ways for particles to exist, and so, as the collapse continues, this resistance grows, quietly at first, then more strongly, until it becomes powerful enough to do something remarkable. It slows the collapse, and then, in a brief, almost imperceptible moment, it stops it, but not gently, because everything has been moving inward so quickly that when this resistance finally becomes strong enough, it doesn't just bring things to rest, it causes a kind of rebound, a sudden, sharp push outward from the inner core, a moment where the collapse overshoots and then pushes back. This is sometimes described as the core bouncing, and while that word might sound simple, what it represents is extraordinary. Matter that has been falling inward at incredible speed, suddenly meeting a resistance so fundamental that it cannot go any further, and so it pushes back, creating a wave, a shock that begins to move outward through the layers of the star. At first, this shock wave is incredibly powerful. It travels outward, carrying energy, pushing against the material that is still falling inward from the outer layers, but as it moves, it begins to lose strength. The star is vast, and the material it must pass through is dense and heavy, so the shock slows, it weakens, and for a moment, it seems as though it might stall completely, as though the star might simply continue collapsing inward, forming something even more extreme, a black hole. But this is not the end of the story, because those countless neutrinos, the ones that were streaming out of the core during the collapse, are still there, passing through the star, interacting ever so slightly with the surrounding matter, and over time, these interactions deposit just enough energy in just the right places to revive the shock, to give it a second push, a quiet reinforcement, and with that added energy, the shock wave continues outward once more, stronger again, until it finally breaks through the outer layers of the star, tearing them apart in a vast and brilliant explosion, a supernova, an event so luminous that for a brief time a single star can outshine an entire galaxy. But at the centre of this explosion, something remains, something small, incredibly dense, and fundamentally different from the star that came before. The core has survived, but it has been transformed. What was once a region of hot plasma, filled with atoms and radiation, has become something else entirely. A compact object, only a few tens of kilometers across, yet containing more mass than the Sun. A place where matter is packed so tightly that the very idea of individual atoms no longer applies, and as we sit with this image, a city-sized object, holding the weight of a star, another quiet question begins to emerge. If gravity was strong enough to collapse the core so completely, why didn't it continue? Why didn't this object collapse all the way into a black hole? What is it exactly that holds it up? And as we follow that question just a little further, we begin to encounter one of the most subtle and fascinating ideas in all of physics. A kind of pressure, not born from heat or motion, but from the simple fact that, at the smallest scales, particles refuse to be identical. As we remain with that newly formed core, still hot from collapse, still settling into its new state, something subtle but deeply important continues to unfold inside it. Because the transformation we've been watching is not yet complete. Even though the core has already shrunk to a size far smaller than before, and even though the familiar structure of atoms has already begun to disappear, the matter inside is still adjusting, still finding a new balance. And to understand what is happening now, it helps to return, just for a moment, to something very small, to the particles that make up everything we know. In the world around you, matter is built from atoms. Each atom has a nucleus at its center, made of protons and neutrons, with electrons moving in a kind of diffuse cloud around it. Most of the space inside an atom is actually empty. If you could zoom in, far beyond anything visible, you would find that the nucleus is incredibly small compared to the space the electrons occupy. But inside this collapsing core, that emptiness has already been squeezed away. The distances between particles have become so small that the idea of separate atoms no longer really applies. Electrons are no longer free to wander as they once did. They are pushed inward, closer and closer to the protons in the nucleus, and eventually, under these extreme conditions, something remarkable happens. The electrons begin to merge with protons. This is not something we see in everyday life. It requires enormous pressure. But here, inside the heart of a collapsing star, the conditions are just right. When an electron and a proton come together in this way, they form a neutron, a neutral particle, and in the process they release something else, a tiny, nearly invisible particle called a neutrino. Now, neutrinos are among the most elusive particles in the universe. They have almost no mass, they carry no electric charge, and because of that, they barely interact with anything at all. They can pass through entire planets, through stars, even through your own body, without ever being noticed. And yet, in this moment, they play a central role. Because as more and more electrons merge with protons, more and more neutrinos are produced, and these neutrinos do something very important. They carry energy away, quietly, effortlessly, streaming outward in all directions, escaping from the dense core far more easily than light ever could. In fact, most of the energy released during this entire collapse does not emerge as light, or heat, or visible motion. It leaves as neutrinos, an immense, invisible flood, carrying away almost everything. If you were somehow able to witness this event, you would see a brilliant explosion, a supernova lighting up space. But what you would not see is the much larger story unfolding beneath it, a story carried by particles that leave almost no trace, a silent outflow, far more powerful than the light itself. And as this continues, the composition of the core changes more and more. Protons become fewer, electrons become fewer, neutrons become more and more dominant, until eventually, the matter inside the core is no longer arranged as atoms, or even as nuclei surrounded by electrons. It becomes something else, a dense, tightly packed collection of neutrons, with only a small fraction of other particles mixed in. But even here, it's important to pause for a moment, because while we often call this object a neutron star, the name can be a little misleading. It suggests something simple, something uniform, as though the star is made entirely of neutrons and nothing else. But the reality is more nuanced. Even in this extreme environment, there are still traces of other particles, a small number of protons, a sea of electrons, and under certain conditions, even heavier, more exotic particles may begin to appear. So the neutron star is not just a solid sphere of neutrons, it's a layered dynamic system, where different kinds of matter exist under different conditions, all held together by gravity and governed by the rules of quantum physics. And as the core settles into this new state, something else becomes clear. The process of collapse, which once seemed unstoppable, has slowed. Not completely stopped yet, but no longer accelerating in the same way, because the matter inside is changing, becoming more resistant to further compression, more structured, in a strange, unfamiliar sense. And this resistance, this quiet push against gravity, is not coming from heat, not from radiation, but from the nature of the particles themselves, from the fact that neutrons, like electrons before them, cannot all be arranged in exactly the same way. They must occupy different states, different configurations, and as the core becomes more crowded, those available configurations become harder to find, which creates a kind of pressure, a pressure that does not come from motion, but from limitation, from the rules that govern how matter can exist. And this is where the story begins to shift again, because now, instead of asking how the star collapses, we begin to ask how it holds itself up. What prevents it from continuing inward, all the way to becoming a black hole? What creates the balance in a place where everything has already been pushed so far beyond the familiar? And as we move gently into that question, we begin to encounter one of the most beautiful ideas in physics, a form of support not built from energy or temperature, but from the quiet refusal of particles to become indistinguishable from one another. As the core settles into this new state, dense, neutron-rich, and no longer made of familiar atoms, something extraordinary continues to unfold, because the collapse we've been following does not simply end in silence. It reaches a turning point, a moment where inward motion becomes something else. To understand this moment, it helps to imagine everything that has been happening so far as a kind of gathering motion, layer after layer of the star, pulled inward by gravity, the outer regions falling toward the center, the inner regions collapsing even faster, all of it moving in the same direction, inward, but deep at the center, where the density has become almost unimaginable. The rules begin to change. The neutrons that now dominate the core cannot be packed together without limit. As we began to sense earlier, there is a quiet resistance that grows stronger as space becomes more crowded. Not a resistance you could see or touch, but one that emerges from the fundamental behavior of these particles. Each neutron must exist in its own distinct state. It cannot simply overlap perfectly with another. And as the available ways to exist become fewer and fewer, this creates a kind of pressure, a pressure that does not come from heat, but from constraint, from the simple fact that matter cannot be arranged arbitrarily. And as the collapse drives the core to even higher densities, this pressure rises sharply, until in a brief and remarkable instant, it becomes strong enough to stop the inward fall. But everything has been moving so quickly, so forcefully, that stopping is not enough. The motion overshoots, and what follows is something like a rebound, a sudden push outward from the inner core. This is often described as the core bouncing, and while that word may sound gentle, the reality is anything but. The core has been falling inward at tremendous speed, so when it meets this resistance, the reversal is sharp, energetic, almost explosive in its own right, and this creates a powerful disturbance, a wave that begins to move outward through the surrounding layers, a shock wave. At first, this shock wave carries enormous energy. It travels outward, pushing against the material that is still falling inward from the outer parts of the star. For a moment, it seems unstoppable, as though it will simply tear the star apart. But as it moves outward, it begins to encounter resistance. The outer layers are dense, heavy, still collapsing inward under gravity. And as the shock pushes through this material, it loses energy, slowly at first, then more noticeably, until something surprising happens. The shock begins to stall. It slows down, weakens, and for a brief, uncertain moment, it seems as though it might fail entirely, as though the star might not explode after all. Instead, everything might continue collapsing inward, forming something even more extreme, a black hole. This is one of the most delicate moments in the entire process, a kind of balance point, where the outcome is not immediately obvious. But this is not where the story ends, because those countless neutrinos, the ones produced during the collapse, are still streaming outward from the core, passing through the surrounding layers. And while neutrinos usually interact very weakly with matter, here, in this incredibly dense environment, even small interactions begin to matter. A tiny fraction of those neutrinos deposit energy into the material behind the stalled shock, not all at once, not dramatically, but steadily, gently reinforcing the motion, and over time, this added energy begins to make a difference. The shock regains strength. It begins to move outward again, slowly at first, then with growing momentum, until finally it breaks free, ripping through the outer layers of the star, sending them hurtling into space. And this is the moment we recognize as a supernova, an explosion so bright that for a short time it can outshine entire galaxies. But what we see, the light, the expanding cloud of gas, is only part of the story, because at the center of this explosion, something remains. The core that collapsed and then rebounded has not been destroyed. It has been transformed. What was once a region filled with plasma, atoms, and radiation is now something entirely different. A compact object, only a few tens of kilometers across, yet containing more mass than the Sun, a neutron star, and around it, the debris of the original star continues to expand outward, enriching the surrounding space with heavy elements that may one day become part of new stars, new planets, perhaps even living things. There is something quietly beautiful about that, a sense that even in this violent ending, something new is being created. But if we return our attention to the neutron star itself, another question begins to take shape, because the core has collapsed dramatically. It has reached extraordinary densities, and yet it did not continue collapsing into a black hole. Something stopped it. Something held it up. Not heat, not fusion, not radiation, but something far more subtle. A kind of pressure that comes not from energy, but from the nature of matter itself. And as we follow that idea just a little further, we begin to explore one of the deepest principles in quantum physics, a rule that quietly shapes the behavior of matter from the smallest particles to entire stars, greater than. As the expanding cloud of the supernova continues to drift outward, growing larger, cooling, and slowly fading into the background of space, something much quieter remains behind, at the very center of that explosion, a remnant, small, compact, and almost invisible at first glance. If you were to look at it from a great distance, it might not seem particularly impressive. It would not glow like a star in the usual sense. It would not spread light across space in the same steady way. And yet, this object contains more mass than the Sun, compressed into a sphere no larger than a city, a neutron star. But to really understand what this means, it helps to pause here for a moment and consider something important. Because not every collapsing star leaves behind a neutron star. There are different possible endings, different outcomes, depending on how much mass remains in the core after the explosion. If the core is relatively light, not too massive, the collapse stops early. In that case, the star leaves behind a white dwarf, a dense, stable object supported by a similar kind of quantum resistance, but involving electrons rather than neutrons. If the core is much heavier, if gravity is simply too strong, then nothing can stop the collapse. No known form of pressure can hold it up, and the result is a black hole, a region where gravity becomes so intense that not even light can escape. But between these two extremes there is a narrow window, a delicate range of mass, and it is within this range that neutron stars are born. You can think of it as a kind of balance point. Too light, and the collapse is gentle. Too heavy, and the collapse never truly stops. But in this middle ground, the star finds a temporary stability, a state where gravity is immense, but not yet overwhelming, where quantum effects and the behaviour of matter at the smaller scales are just strong enough to resist further collapse, and this makes neutron stars something quite special. They are not the final endpoint of matter, but they are very close to it. They exist right at the edge, where the familiar rules of physics begin to stretch, but do not yet break. Now, let's take a closer look at this object. Imagine something with more mass than the Sun, compressed into a sphere roughly 20 kilometers across. That's about the size of a small city, if you could somehow stand on its surface, which is not something you could actually do. But if you imagine it for a moment, the experience would be unlike anything else. The gravity alone would be overwhelming. On Earth, gravity gently pulls you toward the ground. Here, it would be billions of times stronger. Every movement would feel impossibly heavy. Every object, unimaginably dense. Even lifting a small object, if such a thing could exist there, would require more force than anything we could produce. And yet, despite this extreme gravity, the neutron star does not collapse further. It holds its shape, maintains its size, because of the balance we've been building toward. But there is more, because the neutron star is not just dense, it is also incredibly dynamic. When the original star collapsed, it was likely rotating, perhaps slowly, gently turning in space. But as it shrank, something important happened. Its rotation sped up. This is a simple consequence of a familiar principle. If you've ever seen a figure skater pulling their arms while spinning, you've seen this effect in action. As their body becomes more compact, their rotation becomes faster. The same thing happens here, but on a much more dramatic scale. As the core collapses from thousands of kilometers across, down to just a few tens of kilometers, its rotation rate increases enormously. What was once a slow spin becomes incredibly rapid. Some neutron stars rotate many times each second, dozens, hundreds, in some cases, even more. And as they spin, they carry with them something else from their previous life, a magnetic field. All stars have magnetic fields, but when a star collapses into a neutron star, that magnetic field becomes compressed, concentrated into a much smaller space. And just like the rotation, it becomes far stronger. So strong, in fact, that it can begin to affect matter in unusual ways. But we'll return to that a little later. For now, it's enough to notice that the neutron star is not just a static object. It spins, it carries intense magnetic energy, it interacts with its surroundings in subtle but powerful ways, and yet, beneath all of this activity, there is still that central question, the one that quietly lingers. Why does it hold together? Why doesn't it collapse further? Because we've seen how powerful gravity can be. We've watched it pull an entire star inward. We've followed the collapse all the way to the point where atoms disappear. So what is it exactly that draws the line here? What sets the boundary between a neutron star and a black hole? There is in fact a limit, a maximum mass. If a neutron star becomes too heavy, if it gathers more material from its surroundings or merges with another star, it can cross that limit. And when it does, the balance is lost. Gravity wins. The star collapses further, beyond the point where even neutron matter can resist, and a black hole forms. But below that limit, the neutron star remains stable, balanced on the edge, held up by forces that do not come from heat or motion, but from the fundamental rules that govern how particles can exist. And this is where our attention begins to turn inward, because if we want to understand this balance, we need to look more closely at what is happening inside the star itself, at the behavior of neutrons under extreme conditions, at the quiet rules that prevent them from being compressed indefinitely. And as we move gently into that deeper layer of understanding, we begin to uncover a form of pressure unlike anything we encounter in everyday life. A pressure that does not come from pushing, but from the impossibility of perfect sameness. If we return now to that compact object at the center of the explosion, still glowing faintly, still settling into its new form, we can begin to look a little more closely at the question that has been quietly waiting for us. Why does it hold together? Because everything we have seen so far suggests that gravity should continue pulling inward, relentlessly, without pause, and yet it doesn't. The collapse stops. The neutron star remains. So what is it exactly that resists gravity here? To begin answering that, we need to shift our attention, just slightly, away from the scale of stars and towards something much smaller, toward the behavior of individual particles. Now, in the world around you, particles often behave in ways that feel familiar. Objects can move freely, they can share space, they can overlap, mix, and blend without much restriction. But at very small scales, the rules are different. Some particles follow a set of constraints that are surprisingly strict, constraints that are not based on force or energy, but on identity. There is a category of particles known as fermions. This includes electrons, protons, and neutrons, and these particles obey a simple but powerful rule. No two identical fermions can exist in exactly the same state, at the same time. Now that idea might sound abstract at first, so it helps to picture it in a more familiar way. Imagine a room, not a large room, but a carefully organised one. And in this room, each person is required to stand in a slightly different position, with a slightly different posture, facing a slightly different direction. No two people are allowed to stand in exactly the same way. At first, this is easy. There is plenty of space. Everyone can find their own arrangement. But as more and more people enter the room, things begin to change. The available positions become harder to find. Each new person must stand in a way that is more and more different from the others, more stretched, more constrained, until eventually the room becomes so crowded that adding even one more person becomes extremely difficult, not because there is a physical wall stopping them, but because there are no more available ways to fit them in. And this is similar, in a very soft, intuitive sense, to what happens with fermions. As they are squeezed closer together, they are forced into different states, different configurations, and those configurations require energy. So the more tightly you compress them, the more energy is stored in the system, simply because of this rule. This creates a kind of pressure, a pressure that does not come from heat or motion or collisions, but from the impossibility of sameness, from the fact the particles cannot all settle into the same lowest energy arrangement, And this pressure has a name. Physicists call it degeneracy pressure, but for our purposes, it can be helpful to think of it simply as a kind of quantum resistance to being crowded. Now, in a white dwarf, this pressure comes from electrons. It is what holds that smaller stellar remnant together. But in a neutron star, things have gone further, much further. The electrons have already been pushed into protons, forming neutrons. So now, it is the neutrons themselves that must obey this rule. And because neutrons are much more massive than electrons, the conditions required to create this pressure are far more extreme. The densities are higher, the compression is deeper, but the principle is the same. As gravity pulls inward, trying to squeeze the star into a smaller and smaller volume, the neutrons resist, not by pushing outward in the way a heated gas would, but by refusing to occupy the same state. And as they are forced into more energetic configurations, this resistance grows stronger, quietly but powerfully, until it becomes enough to balance gravity. And this is the key idea. The neutron star is not held up by heat. It is not supported by ongoing fusion. There is no internal engine pushing outward. Instead, it is supported by a rule about how particles can exist, a rule that becomes relevant only when matter is pushed to extremes. Now, there is something subtle here that is worth noticing, because this kind of pressure behaves very differently from the kinds we experience in everyday life. If you heat a gas, it expands. If it cools, it contracts. Temperature plays a central role, but degeneracy pressure does not depend on temperature in the same way. Even if the neutron star cools over time, even if it loses energy, this pressure remains. Because it is not about how fast particles are moving. It is about how they are arranged, and that makes neutron stars incredibly stable, at least within a certain range. They can cool, they can spin, they can interact with their surroundings. But as long as their mass remains below a certain threshold, this quantum resistance continues to hold them up. And yet, as stable as this might sound, there is still a limit, a point beyond which even this pressure cannot resist gravity, and that limit depends not just on the behavior of neutrons, but on something else as well. Another force, one that operates at even smaller scales, within the particles themselves. And as we move just a little deeper into that idea, we begin to see that neutron stars are not simply balanced objects, but objects that live right at the edge, balanced, but only just. As we sit with this idea that a neutron star is held up not by heat, but by a quiet quantum rule, something else begins to come into view. Because that rule alone, as powerful as it is not the whole story. It explains how matter resists being compressed, but it does not fully explain what happens when matter is pushed even further, beyond the limits where neutrons begin to crowd together in ways that are almost impossible to imagine. To understand that deeper layer, we need to look even closer than atoms, closer than neutrons, toward the forces that act within the very building blocks of matter. Now, inside every atomic nucleus, there is a force that holds things together. It is what binds protons and neutrons, keeping them from drifting apart despite the electric repulsion between positively charged protons. This force is often called the strong nuclear force, and in most everyday situations, it acts over very small distances, quietly holding nuclei together. But inside a neutron star, the situation is very different, because the distances between particles are no longer normal. They're far smaller, so small that particles are pushed into regimes where the behavior of this force begins to change. At slightly larger distances, as this force is attractive, it pulls particles together, helping to bind them. But at extremely short distances, something unexpected happens. It becomes repulsive. It begins to push back, gently at first, then more strongly, as particles are forced closer together than they would ever naturally be. And this repulsion adds another layer of resistance against gravity. Not a smooth, gradual resistance, but one that becomes sharply stronger as compression increases. You might imagine it as a kind of invisible cushion, not soft, but firm, becoming harder and harder the more you press into it. And when we combine this effect with the quantum resistance we explored earlier, something important becomes clear. Neutron stars are not held up by a single mechanism. They are supported by a combination of effects, each one becoming important at different scales, each one contributing to the balance. But even with all of this, there is still a limit, a point beyond which gravity cannot be resisted. No matter how these forces combine, no matter how extreme the internal conditions become, there is a maximum mass, beyond which a neutron star cannot remain stable. Physicists have given this limit a formal name, a long and technical one, but for our purposes it's enough to think of it simply as the maximum mass a neutron star can support. Below this limit, the star can exist, it can spin, cool, emit radiation, and remain stable for millions, even billions of years. But above this limit, the balance breaks. Gravity overwhelms all resistance, and the star collapses further, becoming a black hole. What makes this especially fascinating is how sharp this boundary can be. It is not always a slow transition. It can be sudden. A neutron star that is stable one moment can become unstable the next, if just a small amount of additional mass is added. This can happen in different ways. For example, if a neutron star exists in a binary system, orbiting another star, it may slowly pull material from its companion, a steady stream of gas, spiraling inward, settling onto its surface. At first, this changes very little. The star becomes slightly heavier, slightly more compact. But over time, as more and more material accumulates, it approaches that critical limit, and then, at some point, the balance is lost. There is no dramatic warning, no gradual collapse, just a quiet crossing of a boundary. And the neutron star gives way, collapsing into a black hole. In other cases, two neutron stars may orbit each other, slowly drawing closer over time, their motion creating gentle ripples in space itself, carrying energy away, until eventually they merge, and in that merger, their combined mass may exceed the limit, leading once again to collapse. And what this tells us is something quite profound. Every neutron star you can imagine, every one that exists in the universe is living on the edge, balanced between two possibilities, stable, but only within a narrow range. It is not a final state, not an absolute endpoint, but a temporary arrangement held together by delicate and competing effects. And there is something quietly beautiful in that. The idea that such an extreme object, something so dense, so powerful, so far removed from everyday experience, is still governed by balance, by rules that must be satisfied, by limits that cannot be crossed. Now, as we begin to move away from this question of stability and turn our attention inward once more, another layer of the neutron star begins to reveal itself, because so far we have been speaking in general terms about forces, about balance, about limits. But what does the neutron star actually look like from the outside in? What happens if we begin at its surface and move slowly downward, layer by layer, into its interior? As we follow that path, we begin to discover that this object is not uniform, not simple, but structured, stratified, with each layer holding its own form of matter, its own behaviour, its own quiet complexity. And just beneath the surface, something surprisingly delicate begins to appear, a thin outer layer glowing softly, marking the boundary between the star and the vast emptiness of space. If we now begin to move inward, not from the deep interior this time, but from the outside, something subtle and unexpected begins to appear. Because after everything we have explored, the collapse, the rebound, the immense density, the quiet quantum rules holding everything together, you might imagine the neutron star as something solid and abrupt, a hard surface, a sharp boundary. But the reality is a little more delicate than that. Before you reach the surface of the neutron star, there is a very thin outer layer, an atmosphere. Not like the atmosphere of Earth, not even like the outer layers of an ordinary star, but something far more subtle, far more fragile. This atmosphere may be only a few centimetres thick, perhaps a few metres at most, so thin that, compared to the size of the star, it is almost negligible. You might think of it as thinner than a coat of paint on a cannonball, and yet it plays an important role, because it is through this thin layer that we actually see the neutron star. Now, this atmosphere is made of very light elements, hydrogen, helium, sometimes carbon. These are the simplest building blocks of matter, stripped down to their essentials by the intense conditions of the star. But even here, nothing behaves quite as it would elsewhere. The gravity at the surface of a neutron star is so strong that everything is pulled tightly inward. The atmosphere does not extend outward in a gentle gradient like Earth's. It is compressed, flattened, held close to the surface, almost pinned in place. And beneath this thin layer, the temperature is extraordinarily high, hundreds of thousands, sometimes millions of degrees. Not the kind of heat you would feel as warmth, but a kind of energy that causes the surface to glow in wavelengths our eyes cannot easily see. X-rays, instead of visible light. The neutron star shines primarily in this higher energy form of radiation, a quiet, steady glow, invisible to human vision, but detectable with the right instruments. So when astronomers observe neutron stars, they're often not seeing something that looks like a star at all. They are detecting this faint, persistent emission, filtered through space, shaped by gravity. And that brings us to something else, something subtle, but deeply important. Because the light that leaves the surface of a neutron star does not arrive unchanged. As it climbs away from the star, it must move against the pull of gravity, and in doing so, it loses energy, not in a dramatic way, not suddenly, but gradually, gently, as though the light itself is being stretched. You might imagine it as a traveller climbing uphill, starting with a certain amount of energy, and slowly giving some of it up as the climb continues. By the time the light reaches distant space, it has changed slightly. Its wavelength has grown longer, its energy a little lower. Physicists describe this effect with a technical term, but we can think of it simply as light becoming a little more tired, a little more stretched, as it escapes the gravity of the star. And this effect is not just theoretical, it can be measured. By carefully studying the light that reaches us, scientists can infer how strong the gravity must be at the surface, and from that they can learn about the size and mass of the neutron star itself. So even this thin atmosphere, almost negligible in thickness, becomes a window, a place where observation meets theory, where something distant and extreme becomes just a little more knowable. Now, if we imagine moving past this atmosphere, descending just a little deeper, we begin to reach what we might call the surface. But even here, the word surface can be misleading, because this is not a smooth, simple boundary. It is not like the surface of a planet, or even the outer layers of a typical star. It is something far denser, far more structured, a place where matter has been compressed into arrangements that are both rigid and unfamiliar. And yet, before we go deeper into that structure, it's worth pausing here for a moment, because there is something quietly striking about this outermost layer. After all the violence of the supernova, after the collapse, the rebound, the formation of neutron matter, the neutron star presents itself to the universe with something so thin, so delicate, that it could almost be overlooked. A fragile boundary surrounding one of the most extreme objects in existence. It's a reminder, in a way, that even the most powerful phenomena in the universe often reveal themselves through subtle signals, a faint glow, a slight shift in light, a whisper, rather than a shout. And as we follow this quiet boundary just a little further inward, something much more solid begins to emerge, a layer where matter is no longer thin and fluid, but arranged into a structure of immense strength, a kind of cosmic material, unlike anything we can create on Earth. If we move just a little deeper, beneath that thin, glowing atmosphere, the character of the neutron star begins to change. The softness fades. The fluid, delicate outer layer gives way to something far more solid, more structured, more resistant. This is the crust of the neutron star, and it is unlike anything we have ever encountered on Earth. At first glance, you might imagine it as a kind of metal, dense, compact, perhaps similar to iron or steel. But that comparison only goes so far, because while the crust does share some properties with familiar materials, it exists under conditions so extreme that its behavior becomes something entirely different. Here, matter is compressed to densities far beyond anything we can reproduce in laboratories. Atoms are no longer arranged with spacious electron clouds surrounding them. Instead, the nuclei themselves, those dense centers of atoms, are packed together in a tight, repeating structure, a lattice. You can think of it as a kind of crystal, but not the kind that forms slowly in a quiet environment. This is a crystal forged under immense pressure, each nucleus positioned carefully, locked into place by the forces around it. And moving through this rigid framework are electrons, not bound to individual atoms anymore, but free to move, forming a kind of flowing background that weaves through the structure. If we pause here for a moment and try to picture this, it's almost like a city made of densely packed towers, with something fluid and invisible moving between them. Except here, everything is compressed to such a degree that the distances involved are almost unimaginably small. And as we move deeper into the crust, something subtle begins to happen. The nuclei themselves begin to change. They become richer in neutrons. More and more neutrons are packed into each nucleus as the surrounding pressure increases, because under these conditions, it becomes energetically favourable for matter to shift in this way, to hold more neutrons than it would under normal circumstances, and so, layer by layer, the composition evolves, quietly, gradually. Now, one of the most remarkable things about this crust is its strength. On Earth, we often think of steel as one of the strongest materials we know. It can support weight, resist deformation, hold structures together. But the crust of a neutron star goes far beyond that. It is thought to be the strongest known material in the universe, not just stronger than steel, but stronger by an almost unimaginable margin. If you could somehow compare them, the difference wouldn't be small, it would be enormous. The crust resists breaking, resists bending, even under the immense gravitational forces pressing down upon it. And this leads to a curious and fascinating idea, because even something this strong is not perfectly smooth, not perfectly uniform. There can be tiny irregularities, small variations in height, what we might call mountains. But here, the word mountain takes on a very different meaning. On Earth, mountains rise kilometers into the sky. They are shaped by tectonic forces, erosion, time. On a neutron star, gravity is so strong that anything trying to rise above the surface is pulled back down almost immediately. So these mountains are incredibly small, only a few centimeters high, perhaps even less, and yet, despite their tiny size, they matter because the star itself is rotating, spinning rapidly, sometimes hundreds of times each second. And if the mass of the star is not distributed perfectly evenly, if there are even the slightest asymmetries, then this rotation can produce subtle ripples in space itself, waves that travel outward, carrying energy away. These are known as gravitational waves, but rather than thinking of them in technical terms, you might imagine them as gentle vibrations spreading outward from the star, caused by its imperfect shape. A tiny mountain on an object no larger than a city, helping to send signals across the universe. There is something quietly beautiful about that, the idea that even the smallest imperfection in one of the most extreme objects in existence can have consequences that reach far beyond it. Now, as we continue to move deeper into the crust, the pressure increases further. The spacing between nuclei becomes even smaller. The number of neutrons within them continues to grow, and eventually, we begin to approach a boundary, a threshold where the nuclei themselves can no longer contain all the neutrons they hold, a point where the structure we've been describing begins to change once again, where matter starts to behave in ways that are even less familiar. And as we approach that boundary, something new begins to happen, not suddenly, not dramatically, but gradually, almost quietly. Neutrons begin to slip free. As we continue our quiet descent, moving deeper beneath the crust, the structure we've been exploring begins to reach its limit. Up to this point, matter has still retained a kind of order. Nuclei arranged in a lattice, electrons moving between them, a rigid framework, even under immense pressure. But as the depth increases, so does the pressure, and with that pressure, something subtle begins to change. The nuclei, those dense clusters of protons and neutrons, have been quietly adapting all along, becoming richer in neutrons, holding more than they would ever hold under normal conditions, because here, deep inside the neutron star, it becomes energetically favourable for matter to shift in this direction, to pack in more neutrons, to adjust its internal balance. But there is a limit to this as well, a point where the nuclei can no longer contain everything within them, a threshold. And as we approach that threshold, something begins to happen that feels almost like a quiet release. Neutrons begin to slip free, not in a sudden burst, not as an explosion, but gradually, gently, like drops of water forming and falling from a saturated surface. This is often described as the neutron drip, a moment where the structure of matter changes, not through violence, but through overflow. The nuclei, once able to hold all their components together, now begin to lose their grip on some of their neutrons, and those neutrons, no longer bound within individual nuclei, begin to move more freely. Now, it's important to notice how different this is from the layers above. In the outer crust, everything was still neatly arranged, each nucleus held together, each particle in its place. But here, the distinction begins to blur. We now have a mixture, nuclei that still exist, though altered. Electrons that continue to move through the structure, and now, free neutrons, occupying the spaces between. It's no longer a simple lattice. It's something more complex, more fluid, more layered. If we try to picture it, we might imagine a landscape where solid structures are slowly giving way to something softer, something that flows between them, not entirely liquid, not entirely solid, but somewhere in between. And this transition is not abrupt. It doesn't happen all at once. Instead, it unfolds gradually as we move deeper. More neutrons drip free. The fraction of free neutrons increases. The structure becomes less rigid, less defined, and more interconnected. Now there is something quietly fascinating about this region, because it represents one of the first major boundaries inside the neutron star, a place where matter begins to lose its familiar identity, where the idea of a nucleus as a clearly defined object starts to weaken, and where the distinction between inside and outside becomes less meaningful. But even here, there is still structure, still organization. The nuclei do not disappear entirely. They persist in altered forms, surrounded by this growing sea of neutrons. And this creates an environment unlike anything we experience elsewhere. A coexistence of phases, a blend of solid and fluid behavior. Now, as the number of free neutrons increases, something else begins to emerge, because these neutrons, no longer confined, begin to interact with one another in new ways. They're still subject to the same quantum rules we explored earlier. They still cannot all occupy the same state, but now they are part of a larger, more continuous system, and under the right conditions, they begin to exhibit a remarkable property, a kind of collective behavior, one that allows them to move without resistance. But before we reach that point, it's worth pausing here just for a moment, because the neutron drip region is more than just a physical boundary. It's a conceptual one, a place where matter transitions from something we can easily imagine to something far more abstract, where the idea of individual particles bound neatly together begins to dissolve into a more continuous picture. And there is something almost poetic in that, the idea that as pressure increases, as conditions become more extreme, the distinctions we rely on begin to fade, solid and liquid, bound and free, separate and continuous, all becoming part of a deeper, more unified description. And as we follow this transformation just a little further, moving deeper still, something even more unusual begins to take shape, because the free neutrons, now forming a kind of background throughout this region, begin to behave in a way that feels almost impossible. They begin to flow without friction. As we move a little deeper, past the region where neutrons begin to slip free, something remarkable begins to unfold. At first, it is subtle, easy to overlook. The free neutrons we encountered as drifting between the remaining nuclei seem, at a glance, like just another component of the star, another ingredient in an already complex mixture. But as their number increases, and as the density continues to rise, their behavior begins to change. They begin to move together, not as individual particles, bumping and scattering in random directions, but as something more coordinated, more unified. And under these conditions, something extraordinary becomes possible. The neutrons begin to form what physicists call a superfluid. But rather than focusing on the term itself, it helps to think about what that means in a more intuitive way. Imagine a fluid that can flow without any resistance at all, no friction, no energy lost to heat, no slowing down. If it begins to move, it continues moving effortlessly, forever, unless something interrupts it. Now, in our everyday world, this kind of behavior is almost impossible to imagine. Every fluid we know, water, air, oil, experiences resistance. They slow down. They dissipate energy. But here, deep inside the neutron star, the conditions allow for something different. The neutrons, bound by quantum rules, begin to act not just as individual particles, but as a collective whole, a single, unified state, and in that state, they can flow without resistance. This is one of the most striking features of the neutron star's interior, a frictionless sea, existing beneath a rigid crust, a quiet, continuous motion, hidden within an otherwise solid structure. Now, this alone would already be remarkable, but as we continue to move deeper, the story becomes even more unusual, because the structure of matter itself begins to change once again. Up to this point, we've described nuclei as compact clusters, small, roughly spherical groupings of protons and neutrons, but under increasing pressure, these shapes begin to deform, they stretch, they flatten, they merge. The simple, round forms give way to something more complex, more fluid, more geometric. And this leads to one of the most strangely named phenomena in all of physics, nuclear pasta. Now, the name might sound almost playful, but it reflects something quite real, because the shapes that emerge in this region resemble familiar forms, long strands, like spaghetti, flat layers, like lasagna, tubular structures, and even bubble-like voids, a kind of intricate three-dimensional pattern formed not by cooking, but by the competing forces inside the star. On one side, there is the strong nuclear force, pulling particles together, trying to bind them. On the other, there is electric repulsion, pushing protons apart, and as these forces interact under extreme pressure, they find a balance in these unusual shapes, not perfectly solid, not fully fluid, but something in between, a kind of organized complexity, emerging from simple rules. If we try to picture it, it might feel like a landscape made of intertwined structures, sheets folding into one another, filaments stretching across space, regions of density and void, arranged in patterns that repeat and evolve, and all of this exists within a region only a few hundred meters thick, beneath the surface of a neutron star. Now, there is something quietly profound about this, because these structures, though strange in appearance, may also be incredibly strong. Some studies suggest that nuclear pasta could be among the strongest materials in the universe, even stronger than the outer crust we explored earlier, and this strength may play a role in how the neutron star behaves as a whole, in how it responds to stress, in how it cracks, shifts, or vibrates over time. It may even influence the signals we detect, such as gravitational waves or sudden changes in rotation. But beyond its strength, there is also its beauty, a kind of hidden architecture, formed under conditions so extreme that they reshape matter into something entirely new. It's a reminder that even in the most intense environments, structure can emerge, patterns can form, order can arise from pressure and constraint, and as we move deeper still, beyond this region of flowing neutrons and intricate shapes, something else begins to happen. The remaining nuclei, which have been stretched and reshaped, begin to disappear altogether. The distinction between nucleus and background fades, and matter transitions into something more continuous, more uniform, an environment where the idea of separate structures gives way to something more like an ocean, a dense, quantum ocean where particles move together and the familiar boundaries between them no longer apply. And as we follow that transition, we begin to enter a region where the neutron star becomes something even more unified, where the layers above, with all their complexity, give way to a deeper, more fundamental state. If we drift just a little deeper, past the intricate patterns of nuclear pasta, something begins to simplify, not in the sense of becoming easier to understand, but in the sense that structure itself begins to dissolve. The shapes fade, the layers soften, and the distinct boundaries we've been following begin to disappear. What was once a landscape of nuclei, stretched and arranged into complex forms, now gives way to something more continuous, more unified. Here, in what we call the outer core, matter no longer exists as separate islands. There are no longer distinct nuclei surrounded by spaces. Instead, everything blends together into a dense, flowing medium. You might imagine it as an ocean, but not an ocean of water, not something made of molecules drifting and colliding. This is an ocean of particles, governed by rules that are far quieter and far more precise. An ocean beneath the crust, but an ocean ruled by quantum laws. Now if we pause here and try to understand what this ocean is made of, we find that it is still mostly neutrons. But not only neutrons, there are also small numbers of protons and electrons moving through the system, maintaining a kind of balance. Because even in such extreme conditions, certain relationships must be preserved. Charges must balance. For every positive charge, there must be a corresponding negative one. And so, the protons and electrons, though fewer in number, still play an essential role. But the dominant feature here is the behavior of the neutrons, because in this environment, they are no longer confined, no longer part of individual structures. They move together as a collective, and under these conditions, they exhibit the same remarkable property we began to encounter earlier. They form a superfluid, a state of matter where motion happens without resistance, where flow continues without loss. If you imagine setting such a fluid in motion, it would not slow down, not gradually, not over time. It would continue, quietly, indefinitely. And inside the neutron star, this superfluid fills the outer core, a vast region where motion is smooth, uninterrupted, and deeply coordinated. Now, there is something subtle but important about this, because while we often think of fluids as chaotic, full of turbulence and randomness, this is different. The motion here is not disordered, it is highly structured, guided by quantum rules that ensure coherence across vast numbers of particles. It is less like a stormy sea and more like a perfectly synchronized movement unfolding beneath the surface. And alongside this superfluid, something else exists. The protons, though fewer in number, behave in their own unusual way. They form what is known as a superconducting state. But rather than focusing on the term, it helps to think of what this means in a more intuitive sense. In this state, certain flows of energy, particularly those associated with magnetic fields, can move without resistance. Just as the neutrons flow without friction, the protons allow magnetic structures to exist and move in a stable, organized way. So within this region, we have two overlapping behaviors: a superfluid of neutrons flowing effortlessly, and a superconducting component guiding magnetic patterns, all embedded within a dense background of electrons, maintaining balance. It is a layered system, but not in the rigid sense we saw above. Here the layers are more like interwoven behaviours, different aspects of matter coexisting in the same space, each following its own rules, yet all part of a single unified state. If we try to picture it, it might feel like an ocean where multiple currents flow at once, some visible, some hidden, all moving together without interference. Now, as we sit with this image, there is something quietly profound about it, because this region represents a kind of transition. Above it, matter still held onto structure, shapes, boundaries. Below it, things may become even more uncertain, but here we find a balance, a continuous medium, governed not by classical intuition, but by deeper principles, and it is within this medium that some of the most intriguing behaviours of neutron stars begin to emerge, because even though this region is calm, smooth, and flowing, the star as a whole is still rotating, spinning rapidly, as we explored earlier, and this raises a subtle question. If the interior is a superfluid, flowing without resistance, how does it rotate? Not in the way a solid object would, not as a single unified spin. Instead, something more intricate takes place. The motion organizes itself into patterns that reflect the quantum nature of the fluid, patterns that are not continuous, but discrete. And as we follow that idea just a little further, we begin to uncover one of the most fascinating aspects of neutron stars, a form of motion that is not smooth, but divided into tiny, quantized threads, a rotation that unfolds not as a simple spin, but as a delicate arrangement of microscopic structures working together to carry the motion of the entire star. If we stay with this quiet, flowing interior, this ocean beneath the crust, a new question begins to take shape. Because we already know something important about neutron stars. They spin, sometimes slowly, but often very quickly. Many of them rotate several times each second, some spin hundreds of times, in that same brief interval. And yet, inside them, the matter is not a solid object. It is not a rigid sphere turning as one piece. Instead, much of it exists as a superfluid, a state that does not behave like an ordinary liquid, and certainly not like a solid. So how does something like that rotate? If we imagine a bowl of water and we spin it, the water forms smooth currents, swirling patterns, continuous motion. But a superfluid behaves differently. It cannot simply rotate in a smooth, continuous way. Instead, its motion organizes itself into tiny, discrete structures, thread-like patterns, each carrying a small portion of the overall rotation. These are sometimes called vortices, but rather than focusing on the term, it may help to picture them more intuitively. Imagine an otherwise perfectly still surface, where rotation is not spread out evenly, but concentrated along extremely thin lines, invisible threads, each one representing a tiny unit of motion. Together, these threads form a pattern, a kind of hidden structure within the fluid that allows the entire system to rotate. So instead of a smooth spin, the rotation becomes quantized, divided into these countless microscopic strands, each one steady, each one precise, and together they carry the motion of the entire star. Now, these threads do not exist in isolation. They interact with their surroundings, because above this superfluid, there is still a crust, rigid, strong, structured, and in certain regions, these threads can become anchored, attached, in a sense, to the material of the crust, not permanently, not immovably, but enough to create a connection, a kind of tension between the flowing interior and the solid outer layer. And over time, as the neutron star gradually loses energy, its rotation slows, very slightly, very gradually. But the interior does not always follow this change smoothly, because those thread-like structures, those tiny carriers of motion, can remain pinned in place, holding onto their original state even as the crust begins to slow. And this creates a subtle imbalance, a difference between how fast the outer layers are rotating and how the inner fluid wants to rotate. A quiet mismatch, building slowly over time until eventually something gives. The pinned structures suddenly release. They shift, rearrange, move outward, redistributing the rotation. And when they do, they transfer a small amount of angular motion back to the crust. The result is a sudden change, a tiny increase in the star's rotation rate, a momentary speed up in an otherwise gradually slowing system. This is what we observe as a glitch, a brief, measurable jump in the timing of a pulsar. Now, pulsars themselves are another remarkable aspect of neutron stars. They are rotating neutron stars that emit beams of radiation, often in radio waves, sometimes in X-rays or gamma rays. And as they spin, these beams sweep across space, like a lighthouse, casting a signal that repeats with extraordinary precision. If the beam crosses Earth, we detect a pulse, a steady rhythm, tick after tick after tick, so precise that some pulses rival the accuracy of our best atomic clocks. And when a glitch occurs, this rhythm changes, not dramatically, not chaotically, but noticeably, a sudden shift in timing, revealing something that has happened deep within the star, something invisible but measurable. Now, there is another layer to this story as well, because alongside the superfluid neutrons, the protons in the outer core exist in a superconducting state, and in this state, magnetic fields are not spread out evenly, they are organized, confined into narrow channels, like bundles of lines threading through the star. You might imagine them as thin strands, guiding the magnetic structure through the interior. These are sometimes referred to as flux tubes, but again, the name is less important than the image. The idea that the magnetic field is not uniform, but structured, threaded through the star in a way that mirrors the quantized motion of the superfluid. And these magnetic threads can interact with the rotational threads, influencing how they move, how they pin, how they release, adding another layer of complexity to the behavior of the star. So deep inside a neutron star, far beneath its surface, there is a kind of hidden choreography, a system of threads and channels, shifting slowly over time, occasionally releasing, adjusting, redistributing motion, all of it unfolding silently, without friction, without sound, and yet leaving traces that travel across the universe, tiny changes in timing, signals that reach us as pulses of light. It is a reminder that even in places we can never visit, never touch, never directly observe, there are patterns, processes, structures, and that through careful observation we can begin to understand them. Now, as we step back from this intricate internal dance and look at the neutron star from a distance once more, something else begins to come into focus, because all of these internal processes, all of this hidden motion, manifests outwardly in the signals we detect, in the light we observe, in the ways these stars interact with their surroundings. And as we follow those signals outward into space, we begin to see neutron stars not just as isolated objects, but as active participants in the universe around them. As we ease our way outward, from the quiet choreography deep inside the star, something begins to change in how we experience it, because while the interior remains hidden, inaccessible, beyond anything we could directly observe, the neutron star is not silent. It reveals itself, not through its surface alone, but through signals that travel across space, light, rhythm, energy. And in these signals, we begin to see different faces of the same object, different ways a neutron star can exist and be understood. One of the most familiar of these faces is the pulsar. We touched on it briefly before, but now, from a little distance, we can see it more clearly. A pulsar is a rotating neutron star that emits beams of radiation. These beams are not spread evenly in all directions. Instead, they are focused, channeled, directed along certain paths, and as the star spins, those beams sweep across space. If one of those beams crosses Earth, we detect it as a pulse, a flash, repeated over and over again, steady, precise, like a cosmic clock, tick after tick after tick. Some pulsars rotate slowly once every second or so. Others spin much faster, dozens, even hundreds of times each second. And yet, their timing remains astonishingly accurate, so accurate that for long periods they can rival the precision of our most advanced clocks. There is something deeply calming about that idea, an object so extreme, so far from anything we know, maintaining such a steady rhythm, a kind of quiet heartbeat, echoing across the universe. Now, the reason these beams exist is closely tied to another feature of neutron stars, their magnetic fields. When the original star collapsed, its magnetic field did not disappear. It was compressed, concentrated, strengthened. Imagine taking something spread over a vast space and squeezing it into a much smaller region. Everything becomes more intense, more focused. And in the case of neutron stars, this leads to magnetic fields that are among the strongest known in the universe. In most neutron stars, these fields are already immense, but in some cases, they become even more extreme. These are known as magnetars, and they represent one of the most intense environments we can imagine. In a magnetar, the magnetic field is so strong that it begins to affect matter itself. Atoms, which normally have a roughly spherical structure, can become distorted, stretched, elongated along the direction of the field. Even light, which we often think of as moving freely through space, can be subtly influenced, its path altered, its behavior shaped by the presence of this immense magnetic environment. It's as if the space around the star becomes structured, not just by gravity, but by magnetism as well. And occasionally, this immense field becomes unstable. The stresses build, the structure shifts, and the star releases energy in sudden bursts. These are known as flares. Brief, intense outpourings of energy, far more powerful than anything we typically observe. In one case, a magnetar released a flare so strong that it affected the upper layers of Earth's atmosphere, even though it was tens of thousands of light years away. A distant event, leaving a measurable trace here, a reminder of just how powerful these objects can be. But magnetars are not the only way neutron stars interact with their surroundings. Some exist in pairs, orbiting other stars. And in these systems, something gentle but persistent can occur. The neutron star begins to draw material from its companion, gas, pulled by gravity, spiraling inward, forming a kind of flow toward the neutron star's surface. As this material falls, it accelerates, heats up, and eventually releases energy in the form of X-rays. So instead of a steady pulse, these systems may glow more continuously, radiating energy as matter settles onto the neutron star. These are known as X-ray binaries, and they provide another window into the behavior of these objects. Now there is one more phenomenon, quieter, but equally fascinating, because even the crust of a neutron star, as strong as it is not completely rigid. Over time, stresses can build due to rotation, magnetic forces, internal changes, and when those stresses become too great, the crust can shift, not in the slow, gradual way we might imagine, but suddenly, a kind of starquake, a brief adjustment, releasing energy, sending subtle signals outward. These events may be linked to some of the bursts we observe, especially in magnetars, but even when they are not directly visible, they are part of the ongoing life of the star. A reminder that even in such extreme environments, change continues, adjustment continues, nothing is completely static. Now, as we take a step back and look at all of these behaviors together, the pulses, the magnetic fields, the flares, the X-ray emissions, the subtle quakes, a picture begins to form. The neutron star is not just a remnant, not just a leftover core. It is an active object, a participant in the universe, sending signals, interacting with its surroundings, revealing its nature through motion and light. And yet, despite all of this activity, we are still observing it from afar, interpreting signals, piecing together clues, because we cannot touch it, cannot enter it, cannot directly see what lies within. But through careful observation, through patterns in light and timing, we begin to build an understanding. And as we follow that idea just a little further, we begin to see that even more information can be extracted, not just from what the star emits, but from how it behaves when it interacts with other stars, when it moves, when it merges, when it sends ripples through space itself. As we sit with all these signals, the pulses, the flares, the quiet glow of X-rays, something deeper begins to take shape. Because even though we cannot enter a neutron star, cannot touch it, cannot see directly inside it, we are not completely blind. The universe, in its own quiet way, leaves clues, and by learning how to read those clues, we begin to understand what lies within. One of the simplest clues comes from light itself, not just the fact that neutron stars emit light, but how that light changes over time. Some neutron stars have small regions on their surface that are slightly hotter than the rest, hot spots. As the star rotates, these hot spots move in and out of view, and the light we detect rises and falls in a steady rhythm. By carefully studying this pattern, how the brightness changes, how quickly it varies, how the timing shifts, scientists can begin to reconstruct the shape of the star, its size, its mass, even subtle details about how space itself is curved around it. It's a bit like watching a distant lighthouse and using the pattern of its beam to infer how fast it is spinning and how it is oriented. But here, the analysis is far more delicate, because the light is not travelling through empty, simple space. It is moving through a region where gravity bends its path, where time itself flows differently. So the signal we receive carries within it a kind of fingerprint of the star's gravity. And by decoding that fingerprint, we learn something about how dense the star must be. Now, this might seem like a small step, but it leads to something much larger, because the relationship between a neutron star's mass and its size tells us how matter behaves under extreme pressure. It tells us how stiff or how compressible that matter is, not through direct measurement, but through inference, through careful observation, through patterns in light. And this is where a deeper idea begins to emerge. We are not just observing a star, we are probing the nature of matter itself. Now, there is another way the universe allows us to learn, one that is even more subtle, even more indirect, and that is through gravitational waves. These not waves of light, not something we can see, but ripples in the structure of space itself. When two massive objects, like neutron stars, orbit each other, they slowly lose energy, not through friction, not through contact, but by sending out these ripples, spreading through space. And as they lose energy, they spiral closer together, faster and faster, until eventually they merge. Now, this process is incredibly powerful, but also incredibly delicate, because the details of how the stars deform as they approach each other depend on what they are made of. If the matter inside is very stiff, the stars resist deformation. They hold their shape. If it is softer, they stretch more easily, distorting under each other's gravity. And this difference, subtle as it may be, leaves an imprint on the gravitational waves they produce, a kind of signature. By detecting these waves and analysing their patterns, scientists can begin to infer how the stars responded to each other, how much they deformed, how their structure changed. And from that, they can learn about the properties of matter deep inside them. It's almost like listening rather than looking, feeling the motion rather than seeing it. Now, one of the most remarkable moments in this field came when two neutron stars were observed merging, not just through gravitational waves, but through light as well. A combined signal, a cosmic event, seen and felt at the same time. And from this event, something extraordinary was confirmed. The collision produced heavy elements, gold, platinum, elements that require extreme conditions to form. For a long time, scientists had wondered where such elements come from, and here, in this violent merger, the answer became clear. Neutron stars, when they collide, can forge some of the rarest materials in the universe. It's a striking thought, that the gold in a ring, the elements in everyday objects, may have been created in events like this, moments of immense energy, long before our planet even existed. Now, as we reflect on all of this, something becomes clear. We cannot enter a neutron star. We cannot see its interior directly, but we can learn by watching how it shines, how it spins, how it cools, how it collides. Each signal, each observation adds another piece to the picture, and slowly, patiently, that picture becomes clearer, not complete, not final, but increasingly detailed. And yet, even with all of this knowledge, there remains a boundary, a region within the neutron star where our understanding begins to fade, where the conditions become so extreme that our current theories begin to struggle. And as we move gently toward that region, we begin to enter a space of uncertainty, not confusion, not chaos, but something quieter, a recognition that there are still questions waiting. As we follow this path inward, beyond what we can observe, beyond what we can confidently infer, we arrive at a place where the picture becomes softer, less defined, not because nothing is there, but because our understanding begins to thin, like a landscape fading into mist. This is the inner core of the neutron star, a region where the density rises even further, beyond the already extreme conditions of the outer core. Here, matter is compressed to several times the density found inside an atomic nucleus, a level of compression so great that the familiar descriptions we've been using begin to feel incomplete. Not wrong, but no longer sufficient, because when neutrons are pushed this close together, something important begins to happen. It becomes energetically difficult to keep them as neutrons. The system begins to search for new ways to arrange itself, new forms that might lower the overall energy, and this is where the possibilities begin. One idea is that new kinds of particles may appear, particles that we rarely encounter and certainly do not see in everyday matter. Among these are particles known as hyperons. Now, rather than focusing on the name, it may help to think of them simply as heavier relatives of the particles we already know. Particles that include additional components, allowing matter to reorganize itself under pressure. In this environment, where neutrons are crowded beyond their usual limits, it may become favorable for some of them to transform, to become something slightly different, a different arrangement that eases the pressure. But here, something subtle emerges, because while these particles might help reduce the internal stress, they also introduce a new effect. They tend to make the matter more compressible, softer, and this creates a kind of tension in our understanding, because observations show that neutron stars can be quite massive, more massive than we might expect if the matter inside were too soft. So we're left with a quiet puzzle. On one hand, theory suggests that these new particles should appear. On the other, observation suggests that the star must remain relatively firm. Balancing these two ideas is still an open question, a place where our current models are still being refined. Now, beyond this, there is another possibility, one that reaches even deeper into the structure of matter itself, because neutrons, like protons, are not truly fundamental. They are made of smaller components, quarks, and under ordinary conditions, these quarks are confined, bound tightly together, never appearing on their own. But in the extreme densities of the inner core, it is possible that this confinement breaks down, that the boundaries between individual particles dissolve and the quarks begin to move more freely, not as isolated particles, but as part of a dense, continuous medium. This is sometimes described as quark matter, but again, the term is less important than the image. The idea that the structure of matter itself begins to shift from distinct particles to something more fluid, more unified. Now, this is not the same as the hot, energetic environments created in particle accelerators. This is not a violent, high-temperature state. Instead, it is cold in a relative sense, calm, dense, ordered in its own way. And within this state, new patterns may emerge, forms of organization governed by the interactions between quarks, possibly even phases where they pair up, moving together in coordinated ways, a kind of deeper level superconductivity beyond what we see in the outer core. But all of this remains uncertain. Not because the ideas are ungrounded, but because the conditions are so extreme that we cannot recreate them directly. We rely on theory, on indirect observation, on careful reasoning. And while these tools are powerful, they leave room for multiple possibilities. There may be other states of matter not yet fully imagined, other arrangements that we have not yet discovered. The inner core remains a frontier, a place where knowledge fades into possibility. And there is something quietly fitting about that, because as we have moved deeper into the neutron star, layer by layer, we have seen matter transform again and again, from atoms to nuclei to free neutrons to superfluids to continuous quantum states, each step revealing something new, something unexpected. So it is perhaps natural that at the very center we encounter not a final answer, but a question, a space where understanding is still unfolding, where the universe continues to hold something back, not as a mystery to frustrate us, but as an invitation to keep exploring, to keep asking, to keep listening. And as we gently step back from this deepest region, from this quiet fog at the center of knowledge, we begin to see the neutron star as a whole, not just as an object of extremes, but as a layered system, a structure where each region tells part of a larger story. As we step back now, slowly, gently, from the deepest layers we've explored, the neutron star begins to come into view once more, not as a single idea, not as a single object, but as something layered, structured, quietly complex. From the outside, it may appear simple, a small dim point in space, a faint pulse, a distant signal, but beneath that surface, there is a world, a sequence of transformations, each one revealing something new about the nature of matter. At the very edge, a thin atmosphere, so delicate, it is almost nothing at all. And yet, it is through this fragile layer that the star speaks to us, through light that escapes, slightly stretched, shaped by gravity, carrying with it the imprint of the star's mass and size. Beneath that, the crust, a structure of immense strength, nuclei arranged in a rigid lattice, electrons flowing between them, matter pushed to a state far beyond anything we encounter on Earth, a surface so strong that even the smallest irregularities, tiny rises, can send subtle signals across the universe. And below that, a transition, a boundary where nuclei can no longer hold everything together, where neutrons begin to slip free, where matter starts to soften, to flow, to change. Deeper still, the strange geometry of nuclear pasta, shapes emerging from pressure and force, structures that are neither fully solid nor fully fluid, but something in between, a hidden architecture formed in silence. And then, the outer core, a quantum ocean, a place where matter becomes continuous, where neutrons flow without resistance, where protons guide magnetic patterns, where everything moves together as part of a unified whole. And deeper still, the inner core, a region we cannot yet fully see, where matter may transform again, where new particles may appear, where the boundaries of our understanding begin to blur. All of this, contained within an object no larger than a city, holding more mass than the sun. There is something almost paradoxical about that. The idea that such immense complexity, such profound transformation, can exist in something so small. But perhaps that is one of the quiet lessons of the universe. That scale does not always correspond to depth, that some of the most intricate structures exist in the smallest spaces. Now, as we reflect on everything we've explored, another idea begins to take shape. Because neutron stars are not just objects, they are laboratories, natural laboratories, where the laws of physics are pushed to their limits. In these stars, we see quantum mechanics, not in tiny experiments, but at a scale large enough to shape entire objects. We see gravity, not as a gentle pull, but as a force strong enough to reshape matter itself. We see nuclear physics, not in controlled conditions, but in environments far beyond anything we can recreate. And in bringing all of these together, neutron stars allow us to test our understanding, to ask questions, to refine our theories, to explore what happens when the familiar rules are extended to their extremes. There is also something deeply human in this, the fact that we can learn about such distant, such extreme objects without ever leaving our planet, by watching light, by measuring timing, by detecting faint ripples in space, by listening carefully to what the universe reveals. And through that process, we begin to see connections between the very small and the very large, between the particles that make up matter and the stars that shape galaxies. The same principles that determine how electrons arrange themselves in atoms also play a role in holding up a neutron star. The same rules, applied across vastly different scales. There is a kind of unity in that, a sense that the universe is not chaotic, but structured, not random, but governed by consistent laws, even in its most extreme corners. And yet, as we've seen, there are still places where our understanding fades, where the answers are not yet clear, where possibilities remain open, the inner core still uncertain, the exact behaviour of matter still under study, the boundaries of knowledge still shifting. But perhaps that too is part of the beauty, the idea that there is always more to discover, more to understand, more to explore. Now, as we come to the end of this quiet journey, you might return just for a moment to the image we began with, a point in space, small, distant, easy to overlook, and yet, within that point, an entire world unfolds, a story of collapse and resistance, of transformation and balance, of matter pushed to its limits and held together by the deepest rules of nature. And so, we've reached the end of tonight's exploration. Whether your eyes are still open, or you're already drifting somewhere between waking and sleep, thank you for being part of this journey. If you'd like to return for more quiet wanderings, you're always welcome. Time has a way of slipping past us, but here, in this moment, everything slows, and somewhere out there, in the vastness of space, a neutron star continues to spin, quietly, steadily, holding together against all odds. Sleep peacefully, wherever and whenever you may be.